Okay, go ahead and leave this slide. Okay, so hi everyone, this is Mike Balzer, and let me check my levels here a little bit. Okay, so hi again, this is Mike Balzer, and off to my right is Chris and Dan Kopp, who will be giving the first presentation. I apologize for being late. They didn't get over here until about 5 minutes before we wanted to get in and set up. So I apologize for that. And with that being said, we'll go ahead and go right into our first guest, who is Dan Kopp. So go ahead and take.
Do you care where I'm standing?
Probably right in front here. There you go. Okay. All right. Okay, and you got the laptop up? All right. Go ahead, Dan.
Right. It's always so weird hearing yourself on the microphone.
Yeah, go ahead and turn it
So
on.
I'm a dentist here in town, and Mike asked me to talk a little bit about how we use 3D scanning, 3D printing, 3D design in our office. We are a general dentist practice, primarily and pretty much exclusively sort of restorative dentistry, meaning so we're doing crowns, bridges, restoring implants. Okay. You want me to start over? So I'm a general dentist, and so yeah, feel free to get a little closer. Otherwise, I'll holler a little louder. Okay. Anyway, so we are a pretty much primarily and exclusively restorative kind of practice, like I was saying. So we do crowns, bridges, restoring implants, all the aesthetic stuff. So boiled down, we're doing a lot of kind of building things and lots of things where we use a fair amount of 3D design and printing. And so, if you want to go to the next slide. What we have in our office is called an Tero, and so it's a 3D digital scanner. And so we use that to create digital images that we do the vast majority, well, pretty much all the 3D printing outside our office in different labs, depending on what we're using it for and how we're doing it. And I'll talk a little bit about the alternative of actually printing things in the office as well, because that's getting more and more common now too. So after we are able to take a digital scan with the Tero, we can then send that to the lab, where again it kind of depends on what we're using it for, but that can be digitally designed, or just a model can actually be printed out, and then they can do whatever they would normally do sort of traditionally. And go ahead and go to the next slide. So what I wanted to do is just kind of walk you through day-to-day the main way that we kind of use it, because Mike, again, just kind of asked me to talk about how we actually use it. So with the Tero, again, we take that digital scan, and you can see the picture of the Tero actually in use down below. So it's on a little cart, and it's got a little wand, and it's bouncing light off of the teeth itself. I always think of it as, and kind of describe it to patients as, it's sort of like sonar with light, and that's what it's doing. It's just capturing that and scanning it, just like most of the other ones. One of the things that I really liked about this particular scanner compared to several of the other dental ones is it's actually open architecture. So I can scan something and create an STL file and then do all sorts of different things with it, whereas a lot of the other ones are actually proprietary file types, and you have to use their scanner, have to use their printer, can't do anything else. So that's enabled us to experiment with it a little bit more and do some more sort of interesting things. But go ahead and move on. So the main way that we use it is day-to-day for something, say, like a crown, where if a tooth that needs a crown, it'll be prepared, it gets reduced down to create room for the material. Say we're doing a porcelain crown, we reduce the tooth itself to create room for that porcelain, and then we would take the scan with the Tero, and you scan the tooth you're working on, all the adjacent teeth, and then the opposing teeth as well. And then that way you have a 3D digital model of the tooth that you're working on, the adjacent teeth, and then how everything actually bites together. So what's nice about it is that it's way better for us and kind of way better for whoever we're working on. It's way more comfortable because you don't have that goopy impression material going everywhere. It's not wasting all that material. But the real value, next slide, is that with that image, we can see everything in advance before sending it off to the lab. And what I find to be most helpful, where you can see the colors on the left, it literally measures how much space we have in between the two teeth, so I know if I have enough room, or if really for the material that we're using, in order for it to be strong enough and predictable enough, we need more space. We need to do something else, or any other changes that we might possibly make. Exactly. It's super, super helpful. Which means that everything really is a lot more predictable and a lot more convenient, and everything goes a lot more smoothly. So there's that model kind of floating around of what that looks like. So with the Tero, they mill that model out of a polycarbonate block on a CNC type printer, or it gets digitally designed like it is on the right, and then the crown itself gets milled. So that's something that could be done in the office. We don't do that, and I'll kind of get into that later. But a lot of the labs are able to do that for us. So I may elect to just actually take the scan, have the lab digitally design it, they print it out, they finalize it, and then they send it back to us. There are other, I should mention that although this is how the Tero company prints out those models that then get sent to the lab, there are other companies that do use the SLA-based stereolithography models. So there's a couple different ways to do it. Correct. Yeah, so that's where you're actually bouncing light on it and it's creating it. You can literally see it kind of rising out of the bed of resin. This company uses a mill. Yeah, correct. Yeah, exactly. Yeah, and same thing primarily for most of the porcelain mills. Or the porcelain printers and all the in-office printers. It's all reductive. 20-something years. It's been around for a long time. Up until the last maybe 6 or 7 years, the quality, the preciseness of the scan itself, and the precision of the porcelain that you were able to mill out was not fantastic, though. So thankfully, people continued using it and continued modifying it and continued improving it, but the old generations of them were not particularly good. I mean, every crown just looked like a marble. At this point, they're getting pretty well. You mean in terms of the models, or they're all pretty comparable at this point in time. Yeah. As far as I'm aware, and with the in terms of the materials where you can print out the model, there's still, as far as I'm aware, anyways, there's still no way to print the porcelain other than you have a block of porcelain and then you mill it down. No, it's depends on the machine. There's either 1 or 2 burrs that grind it down. Yeah, exactly. What else was I going to say? I think I was just going to add that so the lab will get that model. They'll build the crown however we want to do it. Sometimes I'll actually even do both if I'm really worried about something being particularly precise. Print the model, print the crown, and then they can finalize it. And again, going back to kind of in-office versus in the lab, the main reason why I don't actually do it in the office is I just prefer to have the lab fine-tuning and customizing the porcelain itself, because it still needs, depending on the material that you use, most of the time it still needs to be milled and then stained, glazed, and fired again. And I just kind of like the lab to do it. It's just a personal preference thing. We can also use it pretty similarly for when someone has an implant, where when, I don't know if any of you guys are familiar with this or not, but there's an implant. If a tooth gets lost, it can be replaced with an implant. Implant goes down into the bone, and then there's what's called an abutment piece over that, and then a crown would go over that. So what's been really nice is now with certain companies, they have a little connector piece that you can put onto the implant so that you can actually digitally scan that. And then that gets sent to the lab. Then the lab has this 3D model of where the implant is, where the teeth are, and so then they can digitally design that abutment piece so everything is custom made, and then either digitally design the crown over that, or more often than not, the way that we end up doing it, because it's a little bit more precise and it just looks nicer, is they'll digitally design the abutment piece out of either titanium or zirconia, and then take that and then custom make the porcelain crown. So there you can kind of see what the lab's able to actually see. I mean, it's an isolated model, but with the teeth and then them designing the abutment piece that goes over the implant itself, and then that's what then gets milled out, and then they fabricate the porcelain crown directly over that in a couple different ways. The other big way that we use the digital scanning and 3D design and 3D printing is with Invisalign. Not an orthodontist, but we do a little bit of Invisalign for certain specific things to just move teeth. But what Invisalign is a series of clear plastic trays. You can see the tray in the upper right there. And so you wear each tray for 2 weeks at a time, and it slowly moves your teeth. Each tray is shaped a little bit differently to slowly move teeth. So the way that we're able to do it with the iTero is we're able to design, or rather scan all the teeth, so then we have a full arch, all the teeth, 3D model. That gets sent to Invisalign, and so they have this digital model, which then they go through all the movements, however, because I can kind of tell them what I want to do and what I'm trying to do. So they design all those movements, and the movements just get broken up into what's actually doable per tray, because there's only a certain amount of movement you can get per tray. And then that generates pretty much automatically how many trays you have and where it gets broken up. So then with those individual stages of all that movement, each one of those is a tray that then gets actually printed out, and that's a stereolithography model that gets printed out there. So then, actually go back to that for a second. If you were to look at one of those trays really closely, you can actually see the individual layers still. They've changed the materials a little bit, so it's gotten a lot less visible, it's gotten a lot better, but you can still kind of see the individual layers. So just to give you an example of someone that, that's actually someone we're still working on, but you can see where he started, so what his teeth actually look like versus just a still of the ClinCheck model, which is the Invisalign software, versus where we're almost done with him on the right, and then same thing with so that's the predicted model and where we ended up, basically. Pretty incredible. So as time is going on, there's definitely more and more companies coming out with different things that they're designing and printing. So the device in the upper right is the first and only, at least that I'm aware of, I'm pretty sure it's the only FDA-approved sleep appliance that is printed. And so the way that works, because it's kind of a funny-looking thing, is that there's a part that goes across the top teeth, part that goes across the bottom teeth, and then that connector on the side actually pulls the lower teeth forward, pulls the mandible forward, opening up the airway back here, opening up that airway for more oxygen to go in. And then there's also a company that we use that actually digitally prints and designs night guards and what are called splints for treating TMJ problems and things like that. And they're way more accurate than the ones that we are designing manually. There is, I did want to touch on a couple other things that we don't necessarily use day to day, or this I don't really use at all, just because it's not what we have in the office. But the in-office mills and scanners, just to give you a sense of kind of what that looks like. And so the mill itself, because you were asking what it looks like, is in the upper left there. And so there's the little robotic arm that comes and kind of spins around. That one's called the Serac. What's really interesting, and you can go to the next slide, is this new newer form of CT scans that's less radiation. You can use it for smaller areas or for sort of the whole head. It's called a cone beam CT. So you can see what the machine itself actually looks like in the upper right there. basically creates a traditional CT 3D image, though. And then if you go to the next one, what's been really interesting has been being able to take the 3D scans that we take intraorally, merge them with the CT scan, so that then you can do a number of different things with that. You can actually, for example, if a tooth has been lost and you're planning on putting an implant in there, you can virtually and digitally design where the implant is going, and it's super helpful to have all that because then you know where sinuses are, you know where nerves are, and things like that, so you can avoid those important things. Digitally design where that implant's going, and then digitally design the crown that's going to go over the top of it. So in the upper right, you can see where the implant's going, that abutment piece underneath, and then literally the crown over it. This technology is still kind of in its infancy, so it's not readily available. So it's not necessarily something we're doing on a day-to-day basis. Actually, go back one. The other thing I was going to mention that's really neat, because then you can go from there and actually print out the guide for actually placing the implant, so it goes where you're planning it. And now they're getting to the point with on that Xerox machine that was on the slide before, you can print that in your office and not even have to send that out to a lab or to a mill, which is pretty incredible. The other thing that's now you can go to that next slide. The other things that are just kind of coming onto the market are being able to print out for someone that's missing lots of teeth and you're not doing implants, partial denture where there'll be a metal frame and then plastic teeth that go on there. There's a company based out of Canada that's just starting to actually print those out, and then one down in LA that's starting to do it too. Although the one in LA is printing out the frame, printing out the casting it, and then making the metal that way. And then there's also a company that's starting to digitally design and print and mill. I think they're using a mill as well, full dentures as well. I have to admit, I've never used either of those services. The denture one's been around for a while, but the partial one I just found out about last week. And that's all I got. No. You got a question, though? So, yeah, you do a little bit. What you end up with more than anything else is you end up with like a little bit of the cheek. You'll get the tongue in there, or it always looks really funny when occasionally it'll get like my finger or something like that. So the way it ends up happening for us is we scan it all, we submit it, and then part of what we pay for is the Tero company. They have a bunch of technicians that will literally clean all that up. And then the other thing that they do is, say for like a crown, where we have this very precise ending of where the crown is going to end, where say the porcelain is going to end and the tooth begins. The way it gets milled is that tooth is actually separate than the other teeth. So the technician will design that so that it gets milled out separately, so it's actually two different pieces and they just click together. In essence, yeah. So then, and I think you can see it on that model back there too, where you can literally pop that tooth out. It's so they can work on it on its own, because they'll usually put wax in there and build that up, depending on what they're doing. Mm-hmm. Mm-hmm. Every office is different. So for us, since we're doing scanning and not doing the actual design and printing for the most part, it's a mix of both. So, say for like the crown, on the tooth itself that I'm working on, I'll almost always be the one doing the actual scanning of that particular tooth, and then one of my assistants will scan everything else. And then I'll come back and look at it, because we can always add scans if we need to get more detail. Or
the 3D design software, is that specifically dental? You were saying that this is an open source.
Yeah, the one we use, most of the design software is not. And it's been a little bit of a challenge. However, there is other design software that I think Mike is going to talk about that he actually uses on a daily basis that is open source, where we can take that STL file, put it into it, and design a crown that looks like a star type thing. Yeah.
Two questions. Do you have a business card?
Yes.
And the second question is, I've been CPAP and suffered for years.
Mm-hmm.
None of the CPAP machines or any of the inserts that I bought commercially work. And I'm really curious.
All right.
I'm wondering if it actually make a difference. And Do you take health insurance?
Well, for the health insurance, the medical insurance, sometimes you actually can bill that for the sleep apnea stuff. Because it's truly a medical problem that sort of happens to have a dental solution. Yeah. So yeah, I'll get that to you, and we'll talk about that too. Go ahead.
So is there any movement for a certification for people that are working in-house in your office if you were going to do all that stuff in-house?
Not that I'm aware of. What is really interesting about it is the way that the scanning software is designed, and a couple different times that I've used the design software, it's pretty intuitive. They've done a really good job of making it very easy to use. I mean, for example, when we bought that Tero, we've had it something like 3 years now. We were up and running on it with it that day.
I was talking the whole process.
Yeah.
You were going to do scan,
Design, mill.
molds,
Yeah.
milling,
There's not any-
analyzing, all that stuff. It seems like that's quite a bit of very particular expertise.
Yeah. Which is part of the reason I like to have the lab do it, because they are certified technicians.
Exactly. So if you were going to a
Yeah.
random dentist that you don't know if they're how good the person is.
You're 100% correct. And I have considered that same thing as whether or not there should be. But right now there isn't. I think with the idea being that if, as the sort of supervising dentist, you should have a pretty good sense of, how that's going to be designed, exactly how you want that to line up, with the two teeth on either side, and exactly how, functionally, how that's going to be in contact when you're biting down and chewing. And one of the things that, with all these digital models, there's definitely prototypes of, but doesn't quite exist yet, because I've never been able to use one yet, but I keep seeing glimpses of it, are sort of digital models where it actually articulates and you can actually mimic the movements in the different directions that your jaw goes, so that you have that to kind of design in. Because the reality is, when you bite and you chew, you're not in this static position. You're going through a bunch of different movements, and that gets exacerbated if you're doing a lot of clenching and grinding too.
So is the reason that you don't do any of that stuff in-house, the stuff that you send out, is that partly cost or?
No, more of a personal preference thing, to be quite honest. And some of it too was when I bought the machine, when I bought the Tero, there were certain things that have changed in the last 3 years, where things have gotten a little bit faster in terms of the middle times and the firing times, where there's the convenience factor of being able to go in, say you need a crown, you go in, and it's done that day. But it does take a long time. And so for our office and our office setup and layout, I didn't think it was going to work out very well. So where it's that kind of issue of like, okay, we're done. We need you to be somewhere for 45 minutes, and you can't be here. And we just didn't have anywhere to kind of move people around. And so you can get creative and kind of move people around, but it was more of a logistics and preference for me personally. I mean, it's something that I think I'm hoping kind of everyone gets. Everyone I talk to that's a dentist, I tell them that this is what they need to do.
But so as far as you know, you think it would be reasonably cost effective if you're going to do that?
It depends on how much dentistry you're doing, but the numbers generally work out where once you're doing enough dentistry, you can actually save money doing it. So for us, if we were to go that way, I probably would actually save a little bit of money.
We've got 3 other speakers, so can we please hold the questions towards the end, please? Georgie, are you there?
Yes, okay, I'm here.
We have that. I think fine. I'll turn myself down.
Stepping up now.
Need a bigger amp if you want better feedback.
I don't know. Just go ahead and shut off. Well, actually, just go ahead.
What's that?
Okay.
That's not gonna work.
Okay. Georgia, can you hear me?
Yes, okay. Right
Okay.
now.
Go ahead and get started.
It's my turn now, is it?
Yeah, we're going to skip Scott. I can't seem to get him. And we'll go ahead with you.
Sorry, I cannot hear you.
Okay. Can you hear me now?
Yes.
Okay. Go ahead and get started. And Chris will run the PowerPoint presentation here, so you'll be able to see it. So I'm going to cut to it now.
Okay, perfect. So I tell you to pass the slides or not? I can share my screen here.
You can share yours as well, correct.
Okay, let's try to share my screen. If it doesn't work, I can tell you to pass the slide to go in front, okay?
Okay, sounds good.
Okay, so let's try it. Is it okay? Mike? Hi, Mike.
Yeah, we're still on
Is
you.
it, is it working?
It is not. We're just seeing you.
Oh, so maybe you can go in front of you in my presentation, okay?
Okay.
Good. So let's start.
Hang on.
Well, good night, everybody. I think that in California it's already night. Here in Brazil is night for a long time. We are already noon, midnight. So it's a pleasure to talk to you, and I'd like to thank Mike and Chris for the invitation, and all of the people that are hearing me now, right now. So I'll try to talk a little bit about what are doing here in Brazil in our research center. The name is Renato Asher Research Center. Can go. Our institute is one of the 17 institutes in the Brazilian Science Technology Ministry. So each of them is dedicated, is focused in one of the approach or objectives, like Amazonia, space, and ours is mainly focused in information technology. Please go ahead. The next one. Our institute is located in a very interesting area. Mainly, we are in the southeastern part of Brazil. As you know, Brazil is almost the same size of USA, so we are a big country also. And, when you take a plane from Brazil to Miami, you are about 5 hours over our territory. So it's a really big country. Next, please. We have many projects with the industry, with the Brazilian Health Ministry, and also with companies like Petrobras. I don't go further on this, but it's just to tell you what's the source of funding. We have also project with Europe, with many international agencies, and that's it. Go ahead, please. Next one. Our lab, we have many machines, like Dan Kopp said minutes ago. We have many machines in 3D, especially in 3D printing. And we have metal technology, we have plastic technology like SLA, stereolithography, or fused deposition modeling, and so on. That's a quite complete lab. We have also software, many kind of software for simulation, and we also developed some kind of software that's a free software for medical image processing. Please, ahead. And I'll talk today about in few words, what's additive manufacturing, what are our medical imaging and applications at CTI, some examples of computer simulations in medicine, what do you think that will happen in the future? And well, my screen went out. Okay, again. And then we'll talk a little bit about bioprinting. That's a new emerging technology for the future. Okay, go ahead, please. what we see here is a mosaic of many technologies that we call them additive manufacturing or 3D printing. Those technologies are based in many different technologies, like I said, plastic, like metals, and today metal is very important, okay, because they are mainly using to produce customized prostheses. That's a new horizon in the medicine, specific medicine. Please go ahead. And we can see this technology also as a material, but also as a dimension, the size of things today. And when you see in your left hand, you see big things like very close to you in University of California, one professor, that's Berezovic's. He's working with trying to construct buildings using this technology. And also in the middle, the meso and macro size, you can see things that happen in our day by day, like objects that you use. And when you go to the right side, you see micro and nano. Micro, it means that we are using two-photon polymerization, that's a resin-based technology that you can create things in the size of microns, a couple of microns. And this is a very interesting technology because you can go in very small details, you can create very complex geometry in very small details. So maybe it can be used for another application like small robots or things like this that can be used in a medicine. See in the middle in yellow dots, you can see are turbines that are completely useful, made of stereolithography, micro stereolithography. And just in the right, you can see some examples. One example of a 2D, it's not a 3D, but I think that a question of time, you see two animals in a cover of National Geographic. This is 11 by 14 microns. It means that people from Almaden Research Center is working with atoms, and then they can create very, very small things. So in the future, we'll be working with the very small things in the size of nano 3D printing. Okay, go ahead, please. Mainly for 3D printing, we can see that mostly today is polymers. Are polymers in the form of liquids, powder, and filaments, and also metals. And the next material that we can use is ceramics. Ceramic is growing very fast in this area, and you have obviously you have composite in the polymers, metal ceramics. This is a different class of material that you can run in those machines. But you can see also biological materials that are being used today. That's the focus for bioprinting, that I will talk some words about that. And also biomaterials. Biomaterials, that means that materials that you can take direct from the machine and install with someone. For a question of time, biocompatibility means that you can have biocompatibility in terms of time. A syringe, for example, that you use, you have short time inside your body when you inject something, but when you put an implant in a bone, for example, you have to last for a long time. So that's completely different material. And in terms also of place you use it, it means that when you are using something that for example, for contact with blood, you cannot use the same material for contact with bone, for example. So this is the meaning of biocompatibility. You can go back again, please. One. You can go back again. Yes. So another one, please. Okay, another one. Next. Next. I think we are going back. front. Okay, again. So we're talking about the technology that if you see in the axis, horizontal axis, we are talking about more natural solution. We're talking about in vertical axis, you are talking about a complex of solution. So what we think that in terms of permanent or temporary implants that you are today is the technology that we use today, you are just the beginning. It means that you have not so a big complexity and not so a natural solution. But when you go to the right side, you can see two different approaches, like scaffolds, that we call it biofabrication, and organ printing. These are new technologies that are appearing in the horizon for organ shortage or substitution of tissues, or even to use for some chemical industry, for example, for testing drugs or some materials like this. And then go, please, at that next one. So the first part of this graph, I can show you that what we're doing at CTI today. Then talk about the CBCT, that's a cone beam tomography. So you can see in this block in the left side up, you see the acquisition of image. So we receive image in our lab that comes from many hospitals in the country. We, in the middle upside, we work using our software in Vesalius that's used to recreate models in STL file that comes from a CT or MRI image. Then we export to a BioCAD that we can model some prosthesis, or we can go in the right side on bottom, we can make some simulations. We can produce these models in the block, in the box in the middle down, and then in the left side down, you can see the use of it of this model in the surgery. So next one, please. It will be more clear in the next slides. So in Vesalius, that's the software we developed. That's a free software. It's a third version. It's been developed since 2001 as a demand of our lab to use this kind of software. So we decided to develop something that's free software. Next one, please. This software is used to see, for example, many structures of your body, many anatomies. You can choose different things to see. I don't go further because I think that Mike will give you a tutorial about one kind of this software. I think that is 3D slices. Is it, Mike? And next one, please. You can see, for example, a volume rendering of air inside your body, that parts that are completely hollow in your body. Go ahead, next one. And then you can see also some tumors, vascularization, in this case, using contrast. So you apply contrast in the patient, you take image, and then you can see some details. Just to give you some small information about our software. Next one, please. This software is being used for all of the world. Right now, we have 512 people using USA, and it can be downloaded from this site, cti.gov.br/Vesalius. Next, please. So remember, we take the image, we work on the image, so what do you do with these? Sorry for these very disgusting images, but this is the reality. So we have to do is to work on some kind of defect or some kind of problem this patient has, and then you see in the right side on top a design of a prosthesis that is made using MRI based in a dura mater, that's a membrane that covers the brain, and also the blue part is a new reconstruction of this skull. You see on the bottom side On the left bottom, you see the surgery. That's a very aggressive surgery. And then the prosthesis in the place and the results on the right side bottom. Next one, please. That's another option. In this case, was a long time ago. It was done in 2007, I think, if I remember correctly. This is a case of a patient that is in growing age, 12 years old, and what we do, what you can do if the patient is still growing. You cannot put something that is stable. You have to think about to create something that can grow with him. So what we came up is an option to create a prosthesis that's made of four different parts, and you can see covering the skull. It's a cranioplasty. You can see that we have three different parts that can slide away according to the movement of each bone of the skull. So the solution was you can see the right side. You can see the simulation, dynamic simulation of the system. That's a prosthesis with impact on it to test the material, computationally test material and the solution. Next one, please. And then you can see the boy just after the surgery and 2 or 3 years after. And now this guy is an adult with all of these things resulted because of this kind of solution. We call it adaptive prosthesis. Next one, please. Just a case of virtual surgery that we have to do before we have to make a real surgery in the patient. So just press enter. Go ahead. So what you did is, can go back, please. One more. One, wait. Another one. So, no, go ahead, please. Sorry. One more. Another one. So what we're doing, we are changing the anatomy, and you see these red pins. They are placed to fix the muscles. Another one, please. Another. And then you see in the middle of this jaw, we create a carbon fiber structure. Another one, please. Another one. Please again. So what we see is a prosthesis that it was made of polymethyl methacrylate with a carbon fiber inside. So it was approved by the ethical committee to implant in the patient, and the idea at that time was to fix the bones that the patient could move the prosthesis for each of the sides. It was done almost 5, 6, 7 years ago. Next, please. Another area what we can do is to take image from the patient. We create, for example, in this case, a maxilla, that's upper jaw. And in this case, what we're doing is using software to simulate the position of the teeth, depending on the situation you are treating this patient. What's the important for this case? The importance is that you can make many tests in the patient and not wait for many years to see the results. It's not completely right that everything will be okay or works exactly the same the model works, but it's a very good approach to understand better what's going on in a long time with the patient. In this case, is a orthodontic treatment. And what we did, we modeled many materials, many different objects in nodes and elements, and we use a finite element software to simulate this. Next one, please. In this case, the same. You have a patient that normally when you have a big jaw, or a small jaw, you have to make some surgery to put in the right position. We call it this osteotomy of the mandibular ramus. What they do is to just to cut the jaw in two different parts and then fix it with some screws. In this case, they use also plates. What we did here, the same patient, the same stand-up patient, that's a real patient, we can make the surgery, a virtual surgery, and we can test different plates for the same patient. That will be never possible operating a patient in a real case. So what we do is to understand better the interaction between the plates and if they are doing the correct job for this place they are installed in the job. And remember that we're talking about models, and like the mathematician George Borg said, essentially all models are wrong, but some are useful. What we are doing today is looking for useful models that we can understand better the situation. Next, please. Those are some hospitals in Brazil and some in our neighbors, including Mexico, that can come to our lab to work for this kind of surgery. Normally, we do 500 surgeries per year as a project, pilot project with the Brazilian Minister of Health. Next, please. Next, please. So what we're looking for is just to avoid this. Next, please. So the technology can give us the better information and try to reduce subjectivity of surgery. Next, please. The next step that we think that will be the future is that in the case of shortage of organs, of tissues, all tissues, you have to go to complex surgeries. And what happens is, in this case is that you can create some structures that can be derived from the cells of the patients. We are talking about biofabrication. So the next, please. Again. What we're looking for is, just back, please. Yes, thank you. So remember, we're talking about biofabrication is two different approaches. One is the scaffolds, another one organ printing. The scaffold is a structure like a plastic or a biomaterial that if you put in your body, you dissolve in some days or some months. And then you have the cells that you put inside this material, we reconstruct. In the case, for example, a tumor in a mandible or a jaw, you can reconstruct this and give back a jaw for this patient. So the question is it possible today? No, it's not. It's just research. In the right side, we are not talking about material that we implant cells. We are talking about some small spheroids that you can put together and they can self-assemble and create some tissues or organs. Next, please. Next one. So here at our institute, we made some work with experimental printers that we can use for produce this kind of scaffolds. Go ahead, please. And you can see in the right side, just one that we are very interested now, that's a small screw machine that you can put material on the beam on top, and you can mix different materials because depending on the material or the possibility to have the materials, it can be degraded in your organism faster or slower. So you can tune the material for the time you want to. Next, please. Or this is our old technology called electric spinning that use microfibers to create, for example, this kind of finger that's just the skin of a finger. Next, please. or mix the both. You can create the big structure and nanofibers that you can improve the quality of cells to attach on the material. Next, please. In this case, we use the sugarcane polymers, a commercial machine that the idea is to have someday. It's not possible today. For example, if you lose some part of a bone, you can recreate the bone, you can plant cells inside and create a construct and then create a new tissue, a new bone for the patient. Go ahead, please. This is the concept of bioprinting. Some small spheroids of cells that you can produce in lab, and then you put together like a paper, ink in a paper, and then create a structure like a vessel or organ or a tissue. The basic part of this technology is already produced. Next, please. So when you're talking about bioprinting, you are talking about mainly information technology. As I told you, many of these steps I showed before is a simulation, production, it's a machine control, it's a imaging, things like this. But mainly, if today, if you have some, can you back please? If you have today the possibility to create in this machine, that's not possible, an organ or a tissue, you cannot implant because you have strong regulation yet. You have to create new standards. You have to create best practice for this in the near future. So even the technology is developed, you cannot implant yet. Next, please. There's a big complexity. If you try to produce organ in the future, you have to create a blueprint of it. So imagine, for example, a liver or some of these small structures. The CAD system of today are not able to represent this kind of complexity. So next. So that is necessary to develop some CAD that can work like this, like our colleagues from Norway. They developed software that can take some image from a CT scan and then create some structure that you can deposit. Next, please. Those are images from our friend from Norway. They produce, for example, a hand with all of the vascularization inside. That's almost the real vascularization of a body. So you can enter and you can see details of a vessel, a small vessel on it. Next, please. So this is a kind of a new kind of software that is appearing today. This is a kind of simulation when you put together these small balls called spheroids. It can mix together and reduce the size. So you have to plan this for your organ or tissue can produce the right size of this organ, considering the shrinkage of these spheroids. Next one. The same. Next one, please. And then what we're talking about in the future is to integrate. Next one. To create this machine that mainly IT, a system that you can have a feedback control system, a chamber environment control, a dispenser control system, online monitoring system, and also, please, again. Next. And then a supervisory system that you can control all of this machine. This is called a bioprinting. This is a DNA of a bioprinting. Next, please. Next. Again, please. This is a bioreactor. After you have an organ, you have to put in bioreactor. So go ahead, please. So you can simulate, for example, what's going on in the fluid going inside this structure. It's a kind of simulation. It uses CFD, that's computational fluid dynamics. Next, please. Those are small structures like a cage that you can put the spheroid inside. What's the idea is that with like hooks and other structure you can put together, and this structure will be glued in each other. For example, if you want cells to stay in some part of the body that cannot leave this part, this is a very, very interesting structure. This is a size of 100 micron. and made of two-photon polymerization. That's a kind of a 3D printing technology. Next, please. This is the real thing. You can see the size, left size, when it's produced. In the right size, the real size, the real thing, real cage, about 100 micron of diameter. Next, please.
Georgia, can you hear me?
Yes, please.
Can we go ahead and start wrapping it up? Are you close?
Sorry?
Are you almost done?
Yes, I'm finished. I'm finished. So the idea is to put these cells inside. Next, please. And then you can see the small ball with the cells inside already in the right size of the screen. Next, please. This, on the end, I can show you that in the future we can see an organ biofabrication line. You have all of this machine already today available, but they are not integrated. Maybe like in a car production, you have organ production in the future. Next one, please. That's already said in my presentation. Next. Next, I have to thank my colleagues in Brazil and outside Brazil. And the next one. Thanks for the attention, and sorry to be so fast in my presentation.
Thank you, Georgia. You may not hear the applause here, but we really
I can hear.
So thank you very much.
Thank you.
I appreciate you coming in, and then we're going to go ahead and move right on to Scott. And if you can hang on, Georgia, we have some question capability at the end.
Okay.
People will have some questions. So our next guest is Dr. Scott Cleos, who is a board certified radiologist from Florida. Is that correct?
Can you hear me, Mike?
I can hear you. Can you hear me?
Excellent. Yes, I can. Yes, I'm a radiologist. I'm an interventional radiologist, actually.
Okay.
We do the surgery of radiology.
So is there a delay? Can you hear us okay?
Yeah, I can hear you. There's a little bit of an echo when I talk. Do you guys hear that, or is that just on my end here?
The echo is probably coming because you're hearing your own voice come back through my mic. So when you start talking, I will shut up.
Okay, excellent. So, can you see me now, or what are you looking at?
We're looking at you now.
Excellent. All right. You know, I was an electrical engineer before I went to medical school. You'd think I'd have this technology stuff down pat, but it still eludes me sometimes. I'm, as Mike introduced me, I'm one of the radiologists here in Daytona Beach, Florida. I'm an interventional radiologist where we use some of the technologies that Dan and Jorge were presenting to actually diagnose illnesses in patients. And it's come a long, long way. I mean, the beginnings were very austere and basic, and it's the same thing we were doing for about 100 years until we actually got into true 3D printing. I'm going to try to bring stuff up here and do this screen share. We'll see how this works. Let's see, if I bring this file up, let's see if this plays here.
Get your back.
Are you seeing that now?
We are not.
How do I get you guys to see? You still seeing me, or?
We're still seeing you.
Let's see here. So if I go screen share, and what do I do after that?
You choose the screen that your presentation's on. Do you have multiple windows?
I do have multiple windows.
Okay. So click on that particular window and press OK.
The only thing I see, okay, let's try that one. Start screen share.
There you go.
Oh, you got it, huh?
Yep.
All right, good. Still learning, still learning. All right, can you guys see that then?
We can see it, but we're also seeing your notes.
Okay. Oh, you got the notes, so it's switched screens. Oh, man, I apologize. See, I specifically moved this over to the other screen so that you guys could see it. How do I turn that screen share off? Now it's off, right?
So do you want to start it on this end?
It's great stuff here. Let me see. Let me see if I can bring it up on the other screen. I had this all set up, ready to go.
Well, we've got your back over here if you want to go ahead and do it this way.
Let's see here. There's a way to play, but anyway, you're just going to have to look at my notes and everything, I guess, here. So we got Röntgen right there. He's the guy that started all this back in 1895. He discovered X-rays.
Scott, we're not screen, not sharing again. How about
right.
we're going
You guys want to do it from there?
Yes.
All right, go ahead and run it from there.
But we can still see you down. There's a little box, so you can still see your head.
Okay. Yeah, there is some way to move this so that I have the screen coming up on the other side, but I'm not sure how to get back to that at this point.
Well, all the videos in that work on this end, so you can see it up, right?
Well, let me just tell you about Röntgen in 1895. He's the one that found X-rays, and the technique that we used to image patients were basically the same until about 1967, and there was a gentleman named Gottfried Hounsfield. And I don't know if you guys have that actual slide that you can show. It should be under Röntgen B. You see that right there? Oh, man. Where are we now? Because I have no idea.
We're on Godfrey Hounsfield.
Gottfried Hounsfield. Okay, go back one slide for me. So, you know, imitation of a standard X-ray is basically you're going to have to project through a 3D object, and then you present that on a sheet of film, and you get a 2D image. And that's the way things were, like I said, for about 100 years until we go to the next slide here, and we got Mr. Hounsfield. And in 1967, he came up with the concept of CT scanning. And we think of 3D imaging as, just go back for me if you could. We think of 3D imaging as something that's relatively new, that this is a concept that came into play in the 1990s, 2000s, and 2010. But actually, the original design team that I had an opportunity to meet back in 2005, when they first conceptualized the whole process of CT scanning, it was questionable how they were going to actually present this data. And 3D was one of the choices that they had, and they showed me some images from about 1969 that actually showed some early 3D images from some of the early CT scans. Now, they were very rough. The problem is that when you do a CT scan, you can have resolution that's higher in the X and the Y planes, which would be like a cross-section through the body, than it would through the Z plane, which is going to be these slices up and down the body. So the voxels, or the volume of tissue that you're imaging, is going to be what we call anisotropic, which means it's not the same in every direction. The advent of what we call isotropic imaging, or isotropic voxels, is what allows us to do everything that Dan and Jorge were showing you earlier. That is true 3D imaging that allows us to take a volume of tissue and reconstruct it in just about any plane that we want. And just to kind of show you guys, I'm going to go and see if I can actually show you a image here. I'm going to move it over to the other screen and then share it and see if I can do this.
Okay. We'll keep this screen up until you can do that.
Yeah, keep that up until I get this over.
And we're on the Godfrey Hounsfield.
Yep, I see that now. All right, I'm going to put it on that screen. I'm going to go to screen share. Okay. Now, do you see what I'm seeing, or?
We do now.
All right, excellent. Now, so if you look at this, this is an axial scan through the abdomen. Okay, this is an actual CT scan through the abdomen starting from the top. And what you're looking at here is basically a patient who's got an abdominal aortic aneurysm. And you can see right here this dilation of the aorta. These are the kidneys right here. And inside of that aorta, we've put a stent graft. This is one of the things that I do. This 3D imaging allows me to measure the size of the aneurysm, and more importantly, allows me to see the vessels that are coming off of that aorta. Because what you want to do is you want to put this stent graft in a position to basically exclude that aneurysm, but you don't want to block vessels like this. These are the renal arteries that are coming off of the aorta, and that can be problematic if you block those. So you can see this stent graft sitting right in the middle, and this is a conduit that allows blood to flow from the heart through the back and then down to the legs. And you can see as I go further down right here that you can see these limbs actually coming into the lower extremities, and this would continue on down the body right there. So, you know, that's how we would present that as a radiologist and look at that. Now, I can also look at that data with 3D reconstruction. And in most cases, that is, you know, of limited utility to me personally, unless I'm actually trying to look to see where the relationship of those arteries are, because, you know, we have the training to figure out where that stuff is in 3D space. But if I bring this back and I show you, you can clearly see the position of this graft, which we can give a different color to, and actually shows up white on the background of the red contrast that we use to opacify inside that vessel. And you can see the relationship of the renal arteries relative to that graft. And as I rotate this 3D image around, you can see how that is effectively excluding that aneurysm. So this is made possible by the advent of true 3D isotropic imaging. And both Dan and Jorge were using this type of information to do what they do. And I got to tell you, you know, my brother's a dentist up in Northern Virginia, and when Dan was talking about the device that they actually use to basically make that crown, it is absolutely mesmerizing. I mean, you guys, if you ever get a chance to go down to Dan's office and see that, it's fabulous. You know, my brother would take these pictures inside the mouth, and he would prepare the root of the tooth that he was going to put a crown on. And that process, they used to have to put a little temporary crown on. They would send the mold off to the lab, and it would take 2 or 3 weeks, and the patient would be walking around with this temporary. My brother sends all that 3D information to this little device, and there's 2 little burrs that come out, and they keep going like this, back and forth and back and forth, and they grind out this perfect cap that basically fits right on top of that tooth, and the patient goes home with a pretty smile. So, you know, this 3D stuff is revolutionizing the way that we actually treat patients and make things happen in almost real time right now. I want to show you another, if I can, video here, and I'm going to try to move this one over as well so we can all see it together. But this is a video that I made for my YouTube site, and it shows you, let me bring that up again. I'm getting better at this, man. I'm starting to figure this out. Let's see.
You have to do it weekly like we do.
I don't know why the colors are all messed up on that. Let me see here. Do you guys have the, oh, here we go. Now it's working. Maybe you got to, you know, as soon as I start the screen share, it kind of distorts the image there. All right. Let's see. Try it again here. Okay, you see that now? All right, so basically what we're looking at is the ear, and this is a 3D model that I used in one of my videos, and what we're looking at right here is the inner apparatus of the ear itself. This right here is your eardrum, okay, or the tympanic membrane, and these are the 3 ossicles that transmit the vibrations from that tympanic membrane over to this area right here. And this apparatus is your vestibular cochlear system. The cochlea is this curled part that actually processes sounds, and the high-pitched sounds are processed right in the tight coil up here in the middle of the cochlea. The lower sounds are processed down here. And the other side of this device is the vestibular system. And you can see these are oriented in 3D space. Here's going to be like, let's say, the X, the Y, and the Z axis. And the reason they're in that position is because this is the apparatus that tells our brain where we are in 3D space, and it keeps us upright. When patients have an inner ear infection and they want to fall over, their eyes are rocking back and forth, it's because of an abnormality right here. This is the 8th cranial nerve coming off of all of this stuff. These two basically areas are contained in the temporal bone, and it's a bony labyrinth that holds fluid, and they should be separated. So I'm going to bring that up a little bit closer. You can see it here. And every time I play it, it stops. See, I can see it, but it's not playing here. All right, well, you can if I play it intermittently, it kind of shows up. But I took everything away except for the vestibular cochlear system. This right here is called the oval window. These are where the pulsations are transmitted through this cochlea, and then they're decompressed through the round window, which is down here. And unfortunately, you're not going to be able to see the video. It looks like it's going to cut off and then come back in, but I'll bring it back in when it moves direction here. There's a little bit of it. So again, you can kind of see in 3D space, here are the 3 semicircular canals right here, which tell us where we are in space. And this is the cochlea, the part that we actually hear with. We'll bring it in a little bit closer. I don't know why that's cutting off, Mike. I apologize.
I actually ran into that some time ago. You normally have to have a full screen of your animation for it to work properly.
Aha, well, maybe that's the problem. Let me see if that works. Yep. I started it over just to see if it works, but that didn't seem to do it either.
Right.
It's that technology I'm still learning. But anyway, okay, so here we are. We have, basically, as I said before, the 3 semicircular canals. Here's the cochlea and the oval window. Now, I'm going to go back and show you guys. This is what I think is really cool, and I know you guys are going to talk about this a little bit later. This is actually a 3D model, and I assume you guys can see me again, right? This is a 3D model that was made from MR data, and a medical student, a friend of mine, actually took that MR data, and he might have sent it to you guys. I don't know who actually does this out there in space and time, but they sent them that information from a high resolution MR image, and they did a 3D printing of that same device that I just showed you. And so this is the actual cochlear vestibular system from an actual person, and you can see, I apologize for the color. When I first printed this, it was white, and when I tried to hold it up in front of this camera, it kind of just white up the camera. You couldn't see any of the details, so I tried to paint it tan, but it came across almost like a parfait treat from Dairy Queen, or maybe something a little more disgusting like a dog would make. So I hope nobody thinks it's too disgusting here to look at. But this is that cochlear system. You can actually hear, and you can see where that oval window is. Can you guys see right here? That's where the oval window, or that stapes, actually fits right on, and that pulsates right here, and that's where we get the sound from. And then this is the semicircular canals like I showed you in the model, and this is an actual model of someone's inner ear. There is a disease process called the superior canal dehiscence syndrome, or Tullio's phenomenon. And I don't know if anyone's ever seen anyone with this particular phenomenon, but you can, like I said before, these two systems are usually separated by a bony partition. And if you get a hole in that partition, that means that the part that we actually hear with communicates with the part that keeps us balanced, right? So what happens in these particular individuals is that if they hear a loud noise, like a boom or something, it actually gets transmitted from the part where we hear from, and it actually goes into the vestibular portion and starts pushing this fluid around. And so what these patients do is they hear a boom from like a firecracker or something, a horn, and they become dizzy and fall over. It's like those sheep. You ever see those sheep that they make a loud noise and they all fall to the ground? I don't know if they've got the same kind of problem, but you know, with this 3D printing, with this actual model that I can hold in our hand, this is a great teaching tool for my patients, because, you know, trying to explain to them what's happening is difficult unless I got a nice 3D model and I can actually hopefully take their actual 3D data and print something for them. And that's where I see medicine really making some advances, is actually in education. I think we're on the precipice of a revolution in education, because, you know, with the 3D technology that we have and with the new technologies that are coming out. I just heard, I read something on that Oculus Rift. I guess you guys have heard about that, correct?
I have a couple.
You have one? That's great. I mean, can you imagine how great that would be to be able to take these 3D images, virtual 3D images, and actually immerse yourself in that 3D image? I mean, I think the possibilities are just dramatic. So, you know, exciting stuff.
And what we would do is essentially you would wear a set, I would wear a set, and then we would be in a virtual room and we could look at the same object together. And then if you had haptic gloves, you'd be able to use those as well. And
yeah, I mean, the possibilities, I mean, I could just imagine. And that's, you know, one of the things that I try to do with my YouTube channel is to try to present 3D, you know, animations and stuff that would take these difficult medical topics and make them presentable. So that was and that's how Mike and I actually met. He saw my YouTube channel. But I think that this is going to take everything to the next step. So, you know, the technology is here. We use a lot of that 3D reconstruction to aid us in diagnosis. Obviously, Dan and Jorge are using it to actually fix patients. We do a little bit of that, but I think the big challenge for us now is going to be actually, you know, imaging patients safely. And you guys have my slides on that if you want to start that up, because obviously I'm not doing a good job with the slide stuff over here. But if you see the slide that says 2007, I think. Can you bring that up?
Yep, hang on a second.
Yeah, I apologize. I didn't give you any heads up on this. You know, with the two screens, I had everything set up so it would be on the same screen. I could have switched all that and made it go to the other screen. I think it would have worked. While we get that up, I'm just going to pull my side up here and see if I can actually switch it. So.
Okay.
Here we go. Here. Let's see what happens if I do this from beginning. Okay. I'm going to try this again and see if it actually lets me do this. Okay, so if it doesn't, just let me know. But from beginning. Okay, can you guys see that?
Yay!
Oh man, I figured it out. All right, better late than never, huh? All right, so this is what's important. You hear in the press right now about radiation exposure, and for good reason, because we're using more and more imaging technology to actually do stuff with patients. And the old, some of the older members of the audience may remember an exploratory surgery. These young people don't even know what that is. Nobody does an exploratory surgery anymore because we have imaging technology that's so advanced that we can see inside the patient. It would actually be malpractice to take someone to the OR without imaging them first. So everyone gets some kind of scan. And in 2007, it was estimated that the average U.S. resident was exposed to 6 times as much radiation from medical devices in 1980. This is 7-year-old data. So, you know, things have changed probably since then. And here's a graph that kind of shows that distribution. In 1987, you can see that the amount of radiation that we were getting from medical exposures was about 15%. Okay, most of it was from inhaled radon. You guys, or some of the people living up north, have to contend with this. With the basements, you get the radon gas in the basements, and then that can be a big problem. 55% back in 1987 was what we were getting from radon for our yearly exposure of radiation. Now roll forward to 2006. This is a big, big difference. In 2006, you can see how much radiation we're now getting from medical imaging. All right, it's 48%. So, the amount of radon and thoron in the atmosphere and in the ambient areas around us, that hasn't changed. That was 55% back in 1987. So what's changed is how much imaging we're doing, and that's now 48%. Half of all that is computerized tomography, so 24% of all that is computerized tomography. So big, big doses from actually computerized tomography itself. And there's a big push to try to image patients effectively, but also safely and responsibly. So annual CT scans. In 1990, we did 13 million CT scans. All right, a lot of CT scans, but nothing compared to what we're doing to nowadays. About 46 million in 2000. In 2006, that was 62 million. It's probably around 70 million right now. And there really wasn't, back in 1990 and 2000, we really weren't worried about dose that much. There were no rules and regulations regarding medical exposure from x-rays, so nobody was really looking at that. And the dose you were giving an adult man that weighed 120 kilos was the same thing that you were giving to a 12-year-old child, and that was overexposing that child. So things have changed since then. Now, just to put everything in perspective, this is a great graph here, and it shows you the relative exposure and how much radiation you would get from the environment as an equivalent. So the first line here is a PA chest film, just a single view of the chest, and this is the dose, which is kind of irrelevant, but it's relative to all the rest is what we're looking at. So the equivalent dose of a single chest radiograph to a radiograph is 1. Understand there's radiation all around us. There's radiation from the atmosphere and the earth and so on. So the equivalent of this dose from a PA chest is the same as about walking around outside for about 2.4 days. Now, the skull radiograph, it's an equivalent of about 5 chest radiographs or 12 days. Go down here to CT scan of the abdomen, and you can see that's the equivalent of 400 frontal views of the chest, or 2.7 years. So you get the same radiation exposure just walking outside for almost 3 years. A significant amount of radiation. Nobody knows how much radiation it takes to actually, induce cancer, so on and so forth, and the general rule is you do what's necessary to treat the patient. The problem is now, with the litigious nature of medicine, people, I think, are over-diagnosing. Patients will come in with a headache on day 1, and the headache doesn't go away, so they come back to the ED, and every time they come back to that ED, they're getting another CT scan of the head. Probably unnecessary. This is the first prototype CT scanner I told you about from Gottfried Hounsfield in 1967. And this is a little video. It's an old one I did, so I apologize. It's kind of choppy. But this was a Dewar, and it contained a radioactive substance called americium. And there was a pinhole in there that allowed a pencil beam radiation to come out the end. And that passed through these objects and hit this detector on the other side. And the way CT scanning works is that basically you had this little pencil beam radiation. You would pass the objects through that radiation beam, and you would rotate 1 degree. And you'd have to do that all around the patient. You'd go around 180 degrees, or these objects, 180. We only go 180 because they're x-rays. They pass through, so everything above 180 would be redundant. And then you can reconstruct that image. And this is the first image that was made at that prototype scanner. Very impractical. It needed to acquire data for 9 days. So you think it's bad going to the doctor's office right now or going to get a CT scan and holding your breath for 10 seconds. You'd have to hold your breath for 9 days to get an image on this particular prototype right here. It took a supercomputer at the time, back in 1967, about 2.5 hours to calculate this single simple image right here. And the way this works, the way the original calculations were done, it was purely mathematical. You had a whole bunch of unknowns, you had multiple equations, and you would solve those equations. The early design team, or the design team on the early prototypes, figured out there was a better way to do that, and it was called filtered back projection. And what happens is, as you pass through, you get a series of lines that go through the patient, okay, a series of grayscale or attenuations, and these are mapped. Every degree, they're mapped. And what they found is that they could actually take a computer and they could back project these things through the object using a computer, and here's are the different grayscale attenuation, and they could do that. Here I'm not rotating 90 degrees, but it would really be 1 degree. You'd pass the next set through, and you would do it again. You pass it through again, and after you went through 180 degrees, you would reconstruct the image that you started with, including the stuff on the inside. And this process of basically dragging those grayscale images back through using a computer is called filtered back projection. This is the same technique that we use today to basically make a CT image. It hasn't changed in 40 years plus, almost 50 years at this point, filtered back projection. And this is an actual image that I got from the original design team that shows that process in work, in action. And you can actually see all these different projections, these grayscale projections going around 180 degrees, starting right over here. And as it rotates around, you can see we get more and more detail until you get that 180 degrees, and it perfectly reconstructs those objects in the center. So that's filtered back projection, still the same technique we use today. The problem with filtered back projection is it uses a lot of assumptions. But it's very, very quick and very simple to do. This is the first type of CT scanner that we had. They were called the first generation scanners, and they worked just like that prototype, where there was a pinhole and you had a pencil beam source of radiation that passed through that hole, went through the patient, and a single detector on the other side. And this thing would go back and forth. It's called translate, and then rotate 1 degree. Translate, rotate. So these are called translate, rotate scanners. And this scan, to take a single image, it would probably take about 20 minutes. So you had to sit there and you get one single or maybe 2 slices through the brain. You would have to sit there 20 minutes. Just to put that in perspective, now I can scan your whole body in about 30 seconds, from the top of your head down to the base of your toe. So we can do that much, much faster. This is the final generation. It's called helical, where you have no translate component, and it simply goes around and slices the patient up like a spiral sliced ham. And this is a single slice that you're seeing right here in this model. We actually have 64 slice, 128 slice, and some of them actually simulate 500 slices. So you can see that's why I can image you in 30 seconds from head to toe, because I'm cutting you up as you go through the scanner and basically taking a whole bunch of images from it. So the assumptions for filtered back projection is that each and every line passing through the patient is a single beam, okay, just a pencil beam. And it also assumes that the source, the radiation source coming off of your X-ray generator is a point, but actually there's a focal spot that has some geometry. It's actually a circle. You also assume that the detectors are a point on the other side. None of this is true. Okay? None of this is actuality. We actually have some volume to this focal spot. The detectors have volume, so on and so forth. So what we do in order to make this a viable technique, if you have, let's say you're going to shoot a gun and you want to see how accurate it is. If you shoot a whole bunch of bullets, statistically you're going to get around probably where that gun is going to shoot. So you shoot it a whole bunch of times and you'll find out where those bullets are going to end up. The same thing is true here. In order to take into account the geometry of the scanner itself, what we do is we increase the amount of X-rays going through the patient. And statistically, we're going to model this ideal situation with a point source and a point detector and a single pencil beam. What's coming down the pike in short order, and that's called the filtered back projection, by the way. What's coming down the pike is model-based iterative reconstruction. And this is a technique where we're actually going to be able to go in and model the scanner itself. And you have a real focal spot. You got real detectors. You got cubic volumes. The problem with all of this is it gives you beautiful images with much, much less radiation, but it is very, very computationally complex. And today's computers aren't quite there yet. It would take too long to reconstruct those images and actually make them practical. So we're not there at model-based iterative reconstruction, but you're going to see that in very short order. Where we are is in something called statistical iterative reconstruction, and we're using that right now. So let me just show you again. This is how we take into account the problem with modeling an actual system. If you put a whole bunch of x-rays through, the more you put through there, you're going to get a little Gaussian curve here where you're going to have this distribution. Most of them are going to be towards the actual center. To make that more accurate and really find out where our center is, you put in more radiation. So that's what we used to do in the past. The technologists would basically crank up the radiation to get a nice good image on it. This is called adaptive statistical iterative reconstruction, and it's a statistical technique to reduce the amount of radiation. And what it does, instead of the model-based iterative reconstruction I talked to you about before, it actually models the inherent variations in the electronics of the circuit. So we assume that the power source to the X-ray tube is constant, but in reality it fluctuates up and down, which is going to change the actual results that we get. The same thing goes with the detectors, and they have a variation along a central line here. So to take that into account, we increase the photon flux, we increase the amount of radiation. So remember what I said before, with the filtered back projection, you pass those grayscale through the center of the image, and then you go on to the next one. With adaptive statistical iterative reconstruction, you pass one through, you look at the statistical difference between these two, and then you assume what are the variations, a mathematically computational complex process, but then you can go back and you can adjust this pass and pass that back through. So you go back and change your prior passes. And what this does is it allows you to get the same image quality but significantly reduce the dose. So a lot of stuff to assimilate right there, but the Acer, which is a GE construct, and all the other Siemens and Toshiba have their own right now. But what it does is it addresses and reduces the background noise in the electronics and takes those into account. And it should be able to reduce the exposure in patients. And we're using this right now. I mean, in my practice, we have settings on our system that say Acer 10, Acer 20, or Acer 30. And that number following the word Acer is basically the % radiation reduction that you can expect to get. So this is exciting stuff. And I think when we come out with the model-based iterative reconstruction, it's going to be even better. So let me go back here. This is, so that's CT. I wanted to show you guys, are you interested in seeing anything about MRI, or is that going to be too much for the for us to handle right now?
We're running behind, as you know, Scott. So
I can stop right here if you think that's enough then.
I think we can go ahead and stop.
Okay, that's no problem. Sorry about the technical limitations, but you know.
No, we're doing something new now, so I appreciate it. But we got one more guest besides you tonight, so I wanted to get him in. He's got something really interesting to show as well.
Absolutely.
Go ahead and conclude, and gosh, I'm glad that you came and stayed with us.
Oh, thank you for inviting me. I again apologize for the technical difficulty. I didn't even know if I was going to get on tonight. While Mike was preparing you guys for this presentation, I'm texting him trying to figure out how to get onto the system, but it all worked out fine. So I want to thank you guys. Very, very interesting stuff. Dan and Jorge, I learned a lot. I'm looking forward to the last presentation, and hopefully I'll be able to see you guys again sometime in the near future.
And Scott, I think we should do another interview and maybe an intermediate version of this.
Absolutely.
I know some of the techniques you're talking about, and I think NVIDIA with their CUDA cores are going to take care of some of what you're talking about. And they've made some new supercomputers that I think might be interesting in this area.
That's exactly right. That's what's going to drive this technology. Once the computational power of our parallel processors catch up to the technology, then we're going to see some great stuff for sure.
Yeah. Well, again, thank you, Scott.
Thank you.
So we may or may not have time for some questions, but if you want to hang on still, I know it's getting kind of late for you.
Yeah, I'm on the East Coast. We're getting tired, but I'm here for the duration. It's been good so far.
All right, so we'll move on now to Aaron. Aaron, can you hear us?
I can hear you. Can you hear me okay?
We can hear you great. So I brought
Terrific.
Aaron in because Aaron has a very interesting product. It is a anatomical cloud-based web program that allows you to look at the entire body in 3D and literally do a lot of the resections that you saw here on your own. And I will let him take over before I mess it up for him.
All right. Thanks so much, Michael. I appreciate the introduction. I'll start sharing my screen, and we can get right to it. So let's go here, and I'll just share my entire screen. Okay, great. So can you see my screen okay?
Yep.
We can
So
see
this
it.
is. Go ahead.
No, I just said we can see it.
Terrific. So this is the biodigital human. The biodigital human is, we spent about 10 years putting this together. Our company's called Biodigital, biodigital.com, if you want to go on and check it out. And essentially, it's a human body visualization platform. And it's cloud-based, which means that you can access it through the web. We use something called WebGL. WebGL is standard HTML technology, so you don't need a plugin, you don't need to download anything. Essentially, you just go on and use it like you'd use your email. And we've modeled the entire body in very fine detail. We have a team of incredible engineers, and we're constantly refining and improving the body. And so here you can see this is 3D, it's interactive. I'm rotating around, and I can turn on the entire body. We have 6,000 models for both the male and the female. And right now I'm turning on all the male anatomy. And here, if I wanted to, I can turn on the female. And so you can just switch between male and female very easily. You can select objects. I can click on an object and zoom right in. And you can manipulate it. You can configure it however you want. Since it's web-based, you can connect it to a bunch of things. It's not an anatomy program. There are other anatomy programs out there that are 3D. This is a visualization platform for the human body, which means you can actually create your own applications from this. And I'll talk about that a little bit more. But right now, we zoomed into the eye, and there was a lot of talk about craniofacial surgery and craniofacial anatomy. So you have a lot of options. So for example, I can click on the bones of the head, and you can see things got selected in yellow. If I select something, it gets selected in yellow. So if I click on bones of the bones of the head get selected in yellow. And you can see they're hidden by the underlying anatomy. And so if I click transparency mode, you can now see the bones of the head in juxtaposition to the rest of the anatomy. I can also isolate it. So we have all these different visualization modes. I can also start dissecting. So we can just use this as a virtual dissection tool. And I can start to zoom in to the body. And I'm just doing this live in my browser. It's not a video. This is a live demonstration. Hopefully there isn't too much lag. And so I zoomed in right into the pituitary, and I can look around and just go back and forth. And you can see that you have all the anatomy. You can configure it, you can dissect it, you can move around. But our goal is not just to build out anatomy. It's also we're building out conditions. So we're really building out all these various conditions, and we have it organized by group. So for 1 second, I'll just type in heart. And when I type in heart, I'll zoom in, and you can see the heart. Would it be more interesting to see a beating heart? So if I type in beating heart, you can get these dynamic conditions, and now I can see the lungs moving, the heart moving, the diaphragm moving, and I can also do cross sections. it was interesting to hear, Michael was talking about how you use 3D and how it'd be great he was, I guess we're looking at the inner ear. Here we're looking at the heart for a second. But I'll switch to the inner ear. Michael, Scott, I'm sorry, you might be interested to see it later on, some of our 3D models of the inner ear. But you can have this surgical view of the beating heart, and you can watch the heart from all these angles. And this is all done in a web browser. It's also mobile, so if you wanted to do mobile as well, you could do that. So here is just from looking at that from Scott's demonstration a minute ago. I'm going to stream in the inner ear, and here we're looking just at the same models, and you have that three-dimensional view that you were talking about, and you can look at it from all angles. We can also import real data, and not just...
Aaron, there is a little lag, so just keep that in mind.
Okay. So we looked at the inner ear. Right now we're looking at, this is going in slow motion, so no, it's not just lag, maybe it's a little sticky, but you can see this is actual motion capture data that we've imported, and you can see all the muscles dynamically moving. We can make them transparent and look at it, the dynamic motions of the muscle from the real data as it moves around from any angle in a browser. It's also possible, so you can customize all these objects, and then you can save it. You can create an account, and you can save like the dissections and the views you have. So a lot of people create these views from all over the world, and you can see if you click on, you have the conditions tab for all these various conditions, and then if you have community, you have all these various dissections people have made from all over the world. And then you can also create your own private account. We have all sorts of annotation tools. So for example, I can say landmark 1, and then important landmark. And so you can create all these three-dimensional pins in your anatomy. And then you can also save it. So you can save it to your, if you create an account, you can save it and then share it with the world, show whatever your three-dimensional anatomic dissection is, and then you can also create a group, and then that's shareable. You can, three-dimensionally, it's shareable. You can tweet it. As I save this, I'll say 3D session, and I click save, and essentially that will be saved to a database, and it just got saved right there. And now I can share it, I can tweet it, you can embed it into a website. So instead of looking at static images or movies, you can actually have these three-dimensional, dynamic, customized views of the human body. And email it, tweet it, create another link. And we also have more complex tours. Let's see here. And so this is for diabetes. If you want to explain something, we have a tour of diabetes that doesn't have all the complicated UI that the biodigital human has. And you can go in and you can explain some of the most complex, people know about diabetes, but they don't exactly know what's going on here. So we can really explain some very complex subject matter in a three-dimensional dynamic fashion. And this is all interactive. And so you have like a picture-in-picture going from the gross anatomy to the cellular level. And both these windows are interactive. And it's just another interesting way of visualizing the body. We also we have an API for the human body where people have created full-blown surgical simulators. And this is an example of that surgical simulation technology used by a third party. And this is SmileTrain. SmileTrain is a cleft lip and palate organization that teaches doctors in developing countries how to do cleft lip and palate surgery. And so essentially what we've done is we've done these simulations of a full atlas of cleft surgery, and we've broken it down into individual chapters. Oops. And you can go through these very complex procedures. I'll turn down the volume. But I saw Jorge speaking about craniofacial surgery. We're building multiple atlases of surgery, and this has been distributed all over the world, and people are using it. And this is, again, three-dimensional, and there's so much more information, especially when you're talking about surgery. It takes many years and of expertise in standing behind a surgeon's shoulder to really get all that information and to internalize the complexity of 3D surgery. And so I can go from the beginning of a surgery all the way to the end of a surgery. And then this is an environment where there's video and testing. And we have a very powerful analytics engine that allows us to capture what the user is doing, to figure out where they're struggling, and to really use data-driven decision-making to improve our system and to make new modules. So that's essentially, I know I have a very short period of time to speak, so in a nutshell, that's most of my presentation. Oh, one last thing, and Michael and I were briefly speaking about real data and the ability to import real data, and that's something that we're working on right now, is to take CT scans and to take MR or three-dimensionalized data, OBJs and STLs, and be able to import that and save it inside the biodigital human. And this is an example of a patient with a diabetic arm inside the biodigital human, where you can manipulate it. And just a side note, we have been also playing with the Oculus, and it's pretty amazing what you can do. It does work with the Oculus, although that's something that's not out quite yet. But look for it in the future, where you'll have that compatibility of using the biodigital human with something like the Oculus Rift.
Send me a link, Aaron. I'll beta test it for you.
My pleasure.
Okay, well, thank you very much, Aaron, and we'll go ahead and move on right into Chris. And Chris is going to run his own PowerPoint presentation. Yeah, hopefully. So give us a minute to set up. All right. You don't. Turn yourself on, and then I'll give you some audio.
It's on.
Okay, you should have audio now.
I'm on. Yes, I am. I'm just going to turn myself down here, though. I can turn that off. All right. Well, thanks so much for sticking around. I know it's been a long kind of night, and but I'll jump into it and hopefully make it worth your while. Like I said. Oh, here we are. Okay. All right, so just pull me up on screen if you would.
Okay, let's see. Which one you want?
Okay, and again, I'm Chris Kopak. I run a service bureau, parts oven up in Paso Robles, California. So I do 3D printing and rapid prototyping all over the county, actually nationwide now, using FDM technology, which is basically printing plastic. And I have some experience. Hey, Mike, can you pull me up my slides up on the, if you would? So I have some experience. I've been working with a local. I put out a bulletin a few months ago. I was reading about kind of an open source project about prosthetics. You may have seen it in the news, and it was a guy in South Africa that made a hand for for a kid. So I was reading about it and knew about it. So I kind of put out a bulletin locally, and I found a kid, and so we've been working on it recently. It's not finished yet, but I can tell you some of the stuff that I've learned. So kind of my talk is open source additive manufacturing in the new age of prosthetics, and we'll go real quick. So there's an estimated 10 to 15 million amputees worldwide, and just for instance, the price of a new prosthetic leg can cost anywhere from $5,000 to $50,000, but it's not a one-time cost. Typical wear and tear prosthetic leg can last somewhere on average between 3 and 5 years. And this is according to the Hospital of Special Surgery. They're kind of like an online organization that people can find prosthetics people. So for most people on a global scale, prosthetics are completely way out of their ballpark. And when you're talking about a world that we live in where 1 billion people per day are already hungry, you can imagine that this is a prosthetic is typically out of the question. So it's a huge problem going on. So not only that, but everybody is different. So customization is extremely expensive, requires specialists. You know, they have to. They're fabricating. These are some traditional prosthetic legs here over to the right that you may have seen people without legs have, and all the hardware is typically custom made, so they have to machine it. There may be some off-the-shelf components, but you look at, I mean, there's carbon fiber laments that go on. It's extremely specialized and requires an immense amount of knowledge and effort on the and to R&D these projects for big companies to do it. When you're talking about a customized project, you know, these big companies have to spend thousands or millions of dollars developing a new prosthetic design. So it's proprietary systems. It's extremely expensive and hard to make it. So the bottom line, the cost of prosthetics is too damn high. That's pretty much the bottom line. So I think we can do better, and there's a lot of people out there that think we can too. So there's this whole revolution, obviously you know about, that's why you're here, is additive manufacturing. 3D printing is going on. The cost of machines has come way down. Accessibility to the machines. There's a lot of people here that run them in their own. I mean, even Slow Makerspace has one. Mike has, I don't know, you've got about 10 of them now. I've got about 4. And this is actually the machine that I have right here. This is the Fortis 250 here. That's what I have in my office. So it's brought the cost of traditional manufacturing. It's much lower than traditional manufacturing for prototyping or prosthetic work or any of that. Because and it's also much faster because you can take an idea and you can manifest it into reality and have a plastic part in as little as a few hours. So this opens up a whole world of possibilities because your designer the designer of a prosthetic no longer has to be on site. They can essentially take a design and they can send it to across the world to a person to manufacture it. You know, you don't have to have a carbon fiber person sitting there fitting you up. They can take a design. They can send it to some printer like me. You know, so I could have somebody in Australia send me a design. I can print it off. Or in the case that I've been working on recently, this guy's from South Africa, and his designs are openly available online. So one of the benefits is it allows rapid customization, and the timelines are shortened also, so that the access to the patient. The patient doesn't have to wait. Months. Instead, it only takes a few days. So open source is also another big part of the solution. Proprietary systems. Typically, you'll see like a prosthetic project. Even in a big research firm, might have a team of 10 people working on a project. And because it's a highly specialized field, you might only have, like for that prosthetic leg, that new design, only 1 to 10 people working on the design. But in the whole open source movement, that design is freely available online, and there's these repositories where people are critiquing current designs, tweaking current designs. You might have hundreds or even thousands of people working on that same design. So you have a lot more people, and there's other people here that know a lot about open source. I know we have people from the open source community, and it's extremely effective when you're coding for programming, but we're seeing those same benefits downstream in projects like prosthetics. So so open hardware, obviously. Yeah, exactly. So open hardware is definitely we're in this like really unique area right now, or this unique time where patents are going out, and this whole open source thing is like coming in, but at the same time, people want to you need to be compensated to make it a sustainable thing. So people need to be compensated. But we'll get into that. So Um, yeah, yeah, you're right. So one of the benefits is that rather than maybe one like these specialists, rather than spending all their time on designing and customizing these prosthetics, instead they can actually be focusing their time on creating these prosthetics and fitting them to people and rapidly customizing the designs out there. Here's an example. You see the hook, the typical hook you would see for a hand, and then on the left you see this new fingered model. This is a freely available open source design online. It's a fully functional robotic hand that's out there that you can download for free. That's open source, versus one that's thousands of dollars on the right and not very functional. Here's kind of a slide. This is right from Wikipedia. So if you don't know what open source is, I encourage anybody out there to go out there and really research open source. It's a big movement. It's been around for a while, but it's really starting to take off in the last 10 years, last 5 years especially. Software developers are really really on board with this whole idea of open source, because especially in the security world, instead of having 5 people looking at a code base, you can have thousands. So it's starting to have an effect on the additive manufacturing community as well. So a lot of people say, oh, isn't this killing the prosthetics, the people working in it? And so it doesn't mean that people are not being compensated, because you still have, the specialists now still have to be paid to fit and configure the models. It's just changing the way, it's just optimizing the market in a way, So rather than just costing a lot, it's like passing the cost savings on to the patients, which is great. So one of the big ones out there is enablingthefuture.org. If you're interested in 3D prosthetics, go out there, check out enablingthefuture.org. They're dedicated to following the growth of the 3D mechanical hand maker movement. So there was basically a guy in, there was a prop maker in the U.S. who partnered with this guy in South Africa, and they came together and they formed this prosthetic hand for this kid, and it took off from there. Now it's a big movement. They've got all these hands. You can see here some of their models. So they're fully functional models, and they're bringing. You wouldn't even believe how many children are affected by this condition called amniotic band syndrome, where when they're in the womb, a part of them attaches to the placenta and they don't form one of their limbs correctly, and 1 in 1,200 kids is born without a hand. You wouldn't even know, right? But yeah, so it is fairly common to be born without a hand or one of your limbs. I didn't know this until I started reading about this, and I actually met a kid, and now we're building him a hand. So here's some of the hands, and here's some of the volunteers. I'm one of those pins somewhere on that map. Enablingthefuture.org. Here's one of the latest ones. This is up on Thingiverse, MakerBot Thingiverse, so freely downloadable. It's got motors in it and everything. You can actuate the hand. This one's not motors. It's actually mechanically actuated. Here's a great, here's one of my favorite companies that's really inspired a whole new generation of prosthetics. Not Impossible Labs. I would recommend going out and checking out their TED Talks. Incredible TED Talks. And they basically shipped 3D printers, these little maker bots, over to Africa, and because these were kids that were lived basically in Sudan, where they lost limbs either mostly because of minefields. So, and I mean, you could imagine how hard it would be to grow up in the U.S. without a limb. Imagine growing up in Sudan, or imagine having a child without a limb in Sudan. I mean, incredibly hard. So they've done all kinds of other stuff. This one's called the iWriter. They hooked up an Arduino that tracks this guy. He was a famous street artist down in LA, and he had Lou Gehrig's, and he ended up losing all. It just consumed him, and he was confined to a hospital bed, and he essentially couldn't communicate. They made this pair of sunglasses and it could track his eye movement, and he could do art. So he passed away just not too long ago, but he enjoyed the last few bits of his. So now it's evolved into an even like another level of it's brought prosthetics. It's actually giving kids not only the ability to have a functional limb again, but they actually become superheroes. So here's like, this is the latest one. This came out like last week. So it's an actual Iron Man hand. And what's insane about it is it's actually, so it's fully 3D printed, but it actually actuates and becomes the blaster, and then it has like, when the kid folds his hand down, it actually has little LED lights. So not only is it a fully functional prosthetic hand that functions and cheap to manufacture, it actually makes the kid kind of a superhero in class. So here's some open source technologies that haven't. There's a robot hand on the back table back there. If you didn't get a chance to check it out, I made it, but it wasn't my design. The design came from Yale. It's this thing called the Open Hand Project, and it's kind of a mix between FDM technology, which I work in, and then pouring silicone or urethane resins together, using additive manufacturing with traditional manufacturing techniques to make flexures and flexible robotics. But we're starting to see this kind of spill over into prosthetics now. FDM is fused deposition modeling. It's essentially like a hot glue gun. It melts plastic down and lays plastic down layer by layer. Yeah, and then I just wanted to leave you with this kind of. This is one of the. Oh, cannot locate the internet. It says. Oh no. Oh, what did I do? How do I do it? Can you pull it up on there now? I could be done. Or you know what? Just pull up YouTube. Because this is one of the original videos that really got me inspired into the whole prosthetic. You know, really, when I started reaching out to find a kid that I could give a hand, I said, anyone in need of a hand was the poster I put out. It's type in Stratasys Magic Arms. Stratasys is S-T-R-A-S-Y-S. Stratasys. S-T-R-A-T. Stratasys. Let's see. There it is. Here, yeah, let me turn this up.
Ulnar deviation on her hands and rocker bottom feet. The geneticist came upstairs and told us she had arthrogryposis multiplex congenita. They brought her legs down and they casted her, and slowly and surely she started to develop. Our first year with Emma, we found out that there was going to be a conference, and it was in Philadelphia.
It was an arthrogryposis family meeting in Philadelphia where I described the Rex.
We watched a presentation on the Rex.
And that's how it all started.
We ended up in Tarek and Whitney's workshop.
The Rex was attached to a stand, and she was able to put her arms into the Rex and for the first time be able to lift her hand up towards her mouth.
She just started, throwing her hands around and playing.
We were bringing candy up for her to eat. We were bringing toys up there, and it was so fun for us to go up there and see her play.
The existing Rex is all metal parts, and it's kind of big, and Emma was too small for that. So we required something light and small that would attach to her body and go with her. So that's where we had this Stratasys 3D printing machine, and we thought, well, we could print it out for her.
And he did it, and the weight difference is significant. And for a child who only weighs 25 pounds, it makes a big difference. Whitney and Tarek put their minds together and came up with a jacket, and they would put the Rex on that, and we're on our second jacket. She outgrew the first one, and now we're on our second one. And it's still evolving. It's still growing into this incredible prosthetic that helps her to use her arms.
without the 3D printer, we would not be in a position we're in with these younger kids, making them a Rex device that can go with them.
This is one of those industries that matches perfectly with 3D printing, additive manufacturing, because we need custom everything.
I think 3D scanning and printing technology is the future for this field.
The ABS plastic that they use is the same plastic used in Legos. It's human friendly, if you will. It's really strong and durable to handle the abuse. We can answer a need in a heartbeat.
If the Rex breaks, all I have to do is take a picture and email it to Whitney. He knows exactly what the piece is. He prints it out. I go to the hospital, or he's even mailed them.
I don't have to worry about lead time to machine something, order supplies. I can just basically go back to my program and print out another one.
And it's back together and it's working. When she started to express herself, we would go upstairs and we would say, Emma, you know, we're going to put the Rex on. And she called them her magic arms. And everyone in the room cried.
We took it off of her on this one occasion to make some adjustments to it. And as we took it off, she cried out, I want that. And we didn't think all that much of it. But when Mom started to cry, and we look over and ask Mom why she's crying, and she kind of takes a moment to recompose herself and tell us that that was her first complete sentence. To be a part of that, you know, little special moment for somebody else, you know, can't help but kind of tug at your heartstrings.
So it definitely makes prosthetic production just, you know, that much smoother, that much faster, and just kind of. We can make changes really easy, you know, to a model. There's no tooling required, and it definitely has made it. It's making it more accessible for more people. So it's definitely changing the world in a good way. So.
Great.
Yeah.
Thank you.
So thanks for sticking around and joining us tonight.
I thought we'd have 30 minutes of questions, but looks like we may have 5. So who wants to be the first? I have a microphone here, so if there's any of the guests that you'd like to talk to, I believe they're still out there. I've muted them all, but I can turn their mics back on, as well as their heads.
You didn't get Aaron's last name.
I was curious about
You know,
software.
I'll get to that in a moment.
Bill, that actually, the open source software is, what platforms does it run on? Is it Windows only?
Well, there's all kinds of different pieces of software.
The one he was talking about,
I believe it's Windows.
The Invicelius software for DICOM.
Yep, that's it.
Yeah, that one is Windows, but you may be able to run it even
Let's see. Georgia, you still there?
Yes, I'm here.
Here, I'm going to turn my mic off.
The line is certainly a possibility thing, but
Georgia?
Yes.
Okay. We have a question. Go ahead.
does the code for the Invicelius software, whatever, does that lend itself to maybe a cross-platform migration, or if you thought about doing a Linux version or something?
Georgia, can you hear us? There we go.
Yes, okay.
Yeah, I can see you. So the question was...
Yeah, I was wondering if your software was at some point maybe intended for another platform besides Windows. What's the source code? Is it potentially migratable to Linux or anything like that?
You're going to have to kill that mic.
Can you hear us?
No, unfortunately not.
No?
There's a Mac. That's a different piece of software for Windows. side streets. And look at those files. Way back, it's good. Send this to-
Yes. Yeah, he should be able to. Georgia, you can hear us, right?
Yes, I can hear. I can hear you.
Okay. The question was, is the Basilius available on more than the Windows platform? Is it also on Linux?
Please say again, if it's available for, which is available? The software? Envasados? Hello?
Yeah.
So I didn't catch
No.
Actually, run the mic. Yeah, we're not working out too well here. We're getting feedback, and you're probably hearing it as well.
Yeah.
So that particular end didn't work out. So I'll tell you what, I will make sure that all the email addresses, so if you send me an email personally, I'll make sure that they can get back with you. Georgia is really good in responding, and hopefully we can do another interview shortly. And if you send me some of the questions, I'll ask him as well. So again, thank you, Georgia, thank you, Scott, and thank you, Aaron. I appreciate your time, and we're going to go ahead and close down because we're probably going to seize all my stuff and prevent me from taking it home. So I better hurry up. I don't know. Okay. So thank you again, and we're shutting down. This is Mike Balzer and Chris Kovac from All Things 3D, and we appreciate you coming in and taking part in our seminar and presentations.
Thanks so much.
Thank you.
Thank you very much.
For coming, really appreciate it.